What's going on in the universe of the universe?
Well, Brady, there's been a couple of recent results that have been published, which I think are pretty interesting. They concern what the universe is made of and what it's doing. So I thought we could talk about them. I think one is sort of saying everything as it should be, stay calm. The other is like, oh wow, something big's maybe happening here. Start getting excited if you're a theorist. And so I thought we'd try and place them in some sort of perspective and just describe them a little bit. Let's remind ourselves of what we think the universe is made of. Okay, the universe is here, we're in it, but it's very big and it's made of lots of different things. You and I, and the particles that we're made of we kind of club them together and we call them baryons. They make, if you add all the masses or all the energies of everything that makes up the universe together to make it to one, just we normalize it so it's all to one, then the baryons are about 5% of that. You and I make up no more than about 5% of the total energy content of the universe.
Is this like atoms or protons? Or...
Absolutely. Atoms, protons, electrons, light, and everything you can see around you. It's a negligible amount. Well, it's an important amount because we wouldn't be here without it, but it's about 5%. About 25% or so is thought to be in what we call cold dark matter. We've never seen it, but an individual cold dark matter particle, we don't know what it is. We've looked for it, we're still looking for it, and we've got lots of ideas on trying to find it, whether it be direct detections underground or through the Large Hadron Collider looking for effects, or indirectly from things emitting from galaxies, but we've not been able to pick out an individual particle. But the way light gets bent as it passes through galaxies and clusters of galaxies seems to indicate that it has to be there. It's about 25% of the total energy content of the universe.
So when you're talking about the universe, I think of mass, like how kilograms and of us, but even that you measure in energy.
Yeah, people tend to measure things in terms of energy. We can convert it to mass. It becomes a ginormous number. In my head, I'm thinking E equals mc squared. So c is the speed of light, which is a constant. So E, energy, is the same as mass. That is what we tend to think about when we say things in terms of energy. We're really meaning mass, as you say.
Okay, so we've got to 30% with the
we've got to
baryons.
30%. So we've got to the galaxies and the structures of galaxies, but the universe is expanding. Well, that's okay. We thought the universe would be expanding because it began with some sort of big bang. Some initial conditions caused it to expand. But with a universe that's just made up of the matter, it should actually eventually slow down. It should be decelerated. So it's expanding, but it's like someone's putting their foot on the pedal of a car and it's slowing it down, decelerating it.
Why is that? Because everything attracts back to itself?
Everything attracts back, yeah. Gravity sucks.
Right.
Gravity sucks.
So everything gets further away because of the initial propulsion, but then eventually it
slows down because the gravity is sort of saying, whoa, come on, slow down. But in the early 90s, and then in particular about 1998, astronomers looking at, first of all, at clusters of galaxies, but then looking at supernovae exploding in distant galaxies, realized that this can't be right, that the universe has another component in it, and that component, which we've dubbed dark energy, makes up about 70% of this, 70% of this, right? 5% in baryons, 25% or so in cold dark matter, and this stuff is like 70% of the energy content of the universe, and it's not only present, it's driving the universe to accelerate. So the distant galaxies, rather than slowing down, you might think they should, are accelerating apart. Someone's putting their foot on the accelerator, not on the brake.
A couple of quick questions. First, you said 90s and 98. I thought it was like back in the days of Edwin Hubble that it was shown that the universe was expanding.
Sorry, yes. Edwin Hubble showed the universe was expanding. Quite right. In fact, a guy called Slipher, even earlier, may have been sort of the first person to infer there was something going on. But That's different from saying the universe is accelerating.
Oh, right.
So the universe he indeed showed it was expanding and growing, but we thought it was slowing down. And in fact, when I began my PhD in the mid-1980s, everyone said the universe is slowing down. It's late 1980s, early 1990s, and in particular 1998, they realized that it's going whoosh, it's accelerating.
So this 70%, this is the dark energy.
This is the dark energy, and one of the big goals in cosmology now is to try and understand its origin. What is it that's doing it? And it has to have a particular property in order to allow the universe to accelerate. And maybe it's worth, because all of these papers refer to these properties. So the matter that you and I are made of, and radiation, we have both an energy density, energy, and a pressure. So particles hit things. Radiation pressure is something that people at school, children at school, get to see. The photons can get emitted, and the little aluminium foil or gold foil can get pushed up by the pressure of the radiation that's been. So there's a positive pressure pushing out. You and I are made of particles that are not moving very quickly. So then we are non-relativistic. So our pressure is almost zero. We had, the pressure of the particles in this room is not making much impact on the walls of the room, for example. Anything that's got a positive pressure leads to a decelerating universe. It slows it down.
That seems counterintuitive, because you're talking about pushing and impact and that, but you're saying that stops.
Yeah, because the energy that's transferred to it from the expanding universe causes the universe to slow down. Einstein showed us a very important result. That is, the curvature or the expansion of the universe is linked to the matter in the universe. They're not independent of one another. And so if something's happening to the matter, a compensating thing is happening to the expansion of the universe. And so this causes the universe to slow down. But dark energy is a type of energy that has a negative pressure, which is sort of hard to get your head around. But the effect is it feeds back into the expansion of the universe, and it causes the universe to expand. It's sometimes thought of as anti-gravity. I don't like to call it that, but if you think of gravity sucking, then dark energy will try and expand it back out, accelerate it back out again.
So Ed, dark energy has a negative pressure. Does it have a negative energy?
No, it has a positive energy.
So it's not like anti-energy?
No, it's not like anti-energy or anti-mass. No, it's its own thing.
Okay.
And the type of substances that can have this property are, the most famous is the cosmological constant, which we've talked about in the past, that Einstein introduced into his equations, actually to try and stop the universe expanding. But to make it stop, he had to make the universe closed. So our universe is spatially flat, it's just keeping going. He made the universe closed, and by doing that, gravity wants to pull it in, but the cosmological constant wants to push it back out again. And Einstein said, well, there's an equilibrium point where they balance, and that leaves you with a static universe, which is what you wanted. Turns out that's not a good solution. The universe is spatially flat, so the cosmological constant is there, and it's causing, or something like it is there, and it's causing this acceleration. So we have this negative pressure. We have other things that could act like a cosmological constant or act with a negative pressure.
You're talking about the cosmological constant like it's a thing, like it's a kind of particle or a kind of. I always thought because it was a constant, it was just a number, like it was a correction. But But when you say cosmological constant, you're talking about some kind of.
Yeah, we're trying to understand what it is.
It's a thing, though.
In my head, it's a thing.
Right.
And so one of the things that.
So constant's quite a misnomer.
A constant energy density. So some material of some form that has a constant energy density. That is what the cosmological constant is.
Okay. Do scientists have any idea? I mean, you know lots of particles and you know lots of energies and fields, and either real or imagined. What's imagined that could have a positive energy, like all the other energies we know, but somehow has this negative pressure? Has someone come up with that?
So the obvious one is this cosmological constant.
But you don't know what that is either.
I don't know what it is, no.
So that's. I'm talking about what's something that could actually do it. What's a physical particle?
A scalar field, like the Higgs field. we only know one scalar field in nature, but the Higgs field or another scalar field. A scalar field is a field of nature that's just got a value everywhere. It doesn't have a direction, hence scalar. A vector field, like an electric field or a magnetic field, has both a value and a direction. A scalar field is like a temperature, right? A temperature in this room. It can have different values in different parts of the room, but it's a scalar quantity. You don't say it's 23 degrees Celsius in that direction. So a scalar field is a quantity that can have a negative pressure if it satisfies certain conditions on how fast it's moving compared to its energy, its potential.
What do you mean how fast it's moving? Because you said it hasn't got direction.
A scalar field can change in time. Sorry, you're too smart. It can change in time. So, like a temperature, right? Yeah, okay, that's a good example. If I put ice into water, I'll cool the water down. So there's a rate of change of that temperature. That's what I'm talking about. It's with respect to time, not with respect to distance. It's not a velocity.
Okay.
That's a good point.
Okay, so there's some kind of scalar field.
Right, could do it, right? Now, the big question is, what is the dark energy? The best fit models for our universe to date have been a model where you say it's a cosmological constant. So my universe consists of basically four things. It consists of the cosmological constant, it consists of cold dark matter, and it consists of the baryons. And by baryons, I'm clubbing everything in together. It could have a curvature, but the data suggests the curvature is zero. So we've got
three things.
Cosmological constant, cold dark matter, baryons, and curvature.
Oh,
and
right.
I'm saying the curvature looks like it's zero.
Okay.
So it could be that, and the data has been saying that is the best fit. So what do I mean by that? Because we now have a background cosmology, we can solve Einstein's equations, and we can ask what happens in this universe when photons of light pass through it. What happens to those photons if I look far enough back in time to the cosmic microwave background, which it was, just to remind you, the cosmic microwave background was emitted way back about 340,000 years after the Big Bang. Remember, the universe is 13.7 billion years old. It's when the photons decoupled from the particles and just started propagating. That's the cosmic microwave background. And there are slight deviations that you experience in this cosmic microwave background related to the early universe. And these satellites, these amazing cosmic microwave background satellites, have measured these fluctuations. The way the fluctuations change as a function of scale on the universe, where either small scales or bigger scales or all the universe that you can see, depends on your background cosmology. In other words, you can constrain the values of the parameters, cold dark matter, cosmological constant, baryons, by looking at these peaks and troughs in the cosmic microwave background. And the data that fits beautifully is lambda CDM. And in fact, the first paper I sort of want to touch on is the ACT paper, the Atacama Cosmology Telescope, which has just released 6 years worth of data from 2017 to 2022, when I think it stopped operating now. They've analyzed all the data from the cosmic microwave background fluctuations that it can see, and pretty much everything is consistent with this model. And the impact is, I think it's a beautiful piece of work. It's very technical, which way beyond what I understand in terms of how they have done some of the analysis. But their conclusions, they try to let things change from the cosmological constant. So let's call it the lambda CDM paradigm. That's the one that we've been discussing.
Lambda CDM, what does that mean? Is that the four things?
Yeah, because I'm taking the curvature to be zero, but lambda is cosmological constant, CDM is cold dark matter, but the baryons are sort of included in there, right?
So you're saying lambda CDM, this is the understanding of how these four things work in the universe. People like you are constantly twiddling the dials to say, could there be more of this or less of this? But you always have to come back to this touchstone of the cosmic microwave background.
Very good.
And if it doesn't fit that, then it's out the door.
There's this famous quote, right, from Feynman of, you can have the most beautiful mathematical theory in the world, purely elegant, totally elegant. If it doesn't fit the data, it's not right. So you have to come back to the data. Why do people like me not just say something like, well, it's just lambda? Einstein introduced, it's just lambda. Go and do something decent. Go and more interesting. Why are you worried about it? And the reason we're worried about it from a theoretical standpoint is that there are big issues with the value that lambda must have in order to fit the data. There are other processes that occur in nature.
Lambda being the
cosmological constants.
Yeah.
There are other processes that occur in nature which contribute to what lambda should be. And when you calculate them, they're generally way higher than the value of lambda that we see. In other words, the value that lambda would have when we take into account our theoretical models of what we think lambda should be is quite different to what we see. And so some of us think there must be something else going on, that there must be a reason why lambda is playing no role, and that the dark energy has nothing to do with lambda. It's being cared for by something else, and what's actually driving it is maybe one of these scalar fields. And that's where we're looking for what we call dynamical dark energy, because these scalar fields evolve in time. We just discussed it. The temperature changing over time is like the scalar field changing. And so it rolls down its own potential, and its contribution to the dark energy changes over time. So if you had an experiment which could see evidence of this changing over time, it would mean the dark energy isn't a cosmological constant, because the cosmological constant would be constant throughout time. Its contribution would be constant throughout time. If you had this dynamical dark energy, it would change over time. And up until about a year ago, all the data was suggesting there's no evidence for a dynamical dark energy, nothing out there.
Just coming back to ACT for 2 seconds.
Yeah. Well, we can go back from, it's such a good piece of work.
But what ACT did was they used this telescope. Are they more accurately measuring the cosmic microwave background?
Yeah.
Which in turn gives you a more constraining...
Yeah, the data is constraining your model more and more and more. Yeah. And it's worth pointing out, there's been a number of breathtaking cosmic microwave background experiments, and we've discussed them. One is, the original was COBE, which first saw these fluctuations back in the early 90s. Then WMAP, which is a Princeton-led collaboration, saw what we call the acoustic oscillations, these peaks and troughs in the temperature of the microwave background. And then there was Planck. And Planck we did a lot on, where they really found clear evidence for these peaks. And what am I drawing here? I'm drawing the amplitude of the fluctuations as a function of length scale. And large lengths are here on the left, and small lengths are here on the right. And Planck sees big fluctuations on large lengths, and then it gradually comes down, and then eventually their sensitivity drops. I can talk about wave numbers, but there's no need. Now what ACT can do, so Planck's doing large lengths to some intermediate scale here. ACT does this intermediate scale to even smaller scales. So ACT sort of matches onto Planck and then goes further. And so its matching onto Planck is beautiful. It matches really well and then goes further, and it fits beautifully these lambda CDM models. And so they are really constraining these models. They then do what all of us theorists like to do, is we allow the models to fluctuate. We say, imagine the obvious one is, let's imagine the dark energy isn't constant. And so they let it vary. They have some representation of it varying, and they constrain that representation. To my surprise, they do it, and they actually say they have to combine their results with another set of results from DESI, which we're also going to talk about. And when they do, they say there's moderate evidence that the dynamical fit is slightly better than the lambda CDM fit, which I found intriguing. But overall, they said there's no real evidence. It's such a small change that you can't say this is evidence of a better fit. But they allow lots of different things, and the one that I should mention to you is they allow for the dark matter to be axions. So we think of dark matter, conventionally we've thought of dark matter as being WIMPs, weakly interacting massive particles that come linked often to supersymmetry, very massive objects. And we've not seen them, we've not detected them, and so it's caused a shift in the community towards much lighter dark matter particles called axions. So there's a lot of work going on in axions, and then to my amazement, unless I'm misunderstanding it, they're saying in terms of the contribution to dark matter, axion-like particles can only make up about 5% of the dark matter. That could be a really big result, because people are busy looking to see if axions can be all the dark matter. And if there can only be 5%, then the dark matter has got to be something else.
Okay.
I've moved away from the dark energy briefly there.
Okay, so ACT have given us a better idea about the cosmic microwave background, and in turn have let us look more closely at how well our models are working.
Very good.
And they're saying the models are looking pretty good.
They're saying there's no reason to go beyond lambda CDM. That's what their bottom line seems to be to me. Lambda CDM is fitting really well.
Which is what you explained right at the start, though.
Yeah.
Okay. Talk to me about, let's get dynamic.
So let's get dynamic. So a year ago, there's another fantastic experiment. I'm rubbish on experiments, but let me just give you some numbers. There's this amazing result. It's called the Dark Energy Spectroscopic Instrument, DESI. The hint is in the title, right? They're looking for dark energy as well. They have, over the course of 3 years, they have taken spectroscopic details. In other words, measured the light coming and the wavelength of light coming from 30 million galaxies in 3 years, which is just, just think about how many a day they're managing to do. And the reason they can do it is, if I understand right, the plate which collects the light has been designed in such a way, it basically has 5,000 points in it, which they can move around to look at any one time 5,000 different galaxies and take the light from them. And that's one observation, and then, let's do another one. So every time they're doing it's just staggering. So they're looking at these galaxies, which are much closer to us than the CMB is. And from there, they're also trying to infer, by looking at what we call baryon acoustic oscillations, and the baryon acoustic oscillations tell us about the background cosmology. They're looking at these baryon acoustic oscillations linked to these galaxies, and from it, they're trying to infer the cosmological parameters, the lambdas, the cold dark matters. A year ago, they said they've got tentative evidence that the best fit to their models is not a lambda CDM. And in fact, when they fit to lambda CDM, they find real constraints, conflicts, if you like, with the CMB results. And they said the way they can reconcile it is by saying the dark energy isn't a constant, it's evolving, so it's changing over time, and they then constrain the way it changes. They use a particular way of parameterizing it, because we don't know what the dark energy is, so we don't know how it's really changing. So what you try and do is you try and parameterize it. You try and think of possible ways it can change and constrain those possible ways. So they do that. And they said back a year or so ago, it was about we call it a 3 sigma, 2 to 3 sigma. Well, if in the world of particle physics, 3 sigma is, okay, that's interesting, but I'm not going to get too excited. 2 sigma is could go away any day. 5 sigma in particle physics is whoa, detection. Higgs detection was a 5 sigma event. So they have gone on and they've been carrying on doing this analysis. They've now produced their second set of data, and they're now saying the evidence has gone up, depending on which set of data they use, it has gone up to about 4 sigma. Okay, so it's getting more significant. Now, why am I personally would love it if there's dark energy, dynamical dark energy.
What's the claim here, Ed? Is the claim that at different points in time, there's different amounts of dark energy in the universe?
Yeah.
Right. And we all traditionally think energy can't be created or destroyed or go anywhere, and yet at different times there seems to be more floating around.
So the sum of the energies will always be 1. Do you remember the cold dark matter and the baryons and the dark energy? They'll always sum to 1. So that's consistent with it overall not getting changed, but it's how it sums to 1 that's changing. So when it's a cosmological constant, its contribution to this sum evolves in a certain way. So it begins negligibly and then it rises up. But dynamical dark energy will just have a different evolution as it works up to become, it has to look a little bit like a cosmological constant today, because that fits so well the CMB, but earlier on it didn't need to. And it will have a different evolution. And what DESI are claiming is that they can begin to see evidence of this evolution being different to what the cosmological constant is. Now, if that's true, it's amazing. I mean, because it means that there must be something else out there in the universe that we just don't know. We don't know what the cosmological constant is as a quantity, but we know it could be there. Einstein said it could be there. It's in his equations, this thing. But this dynamical dark energy can't be a cosmological constant because it's evolving in time. And the cosmological constant, the energy density of a cosmological constant is constant in time.
And that means it has to be a physically different thing.
It has to be a physically different thing, completely different. And the obvious thing for it to try and be is a scalar field. But there are other possibilities that it could be that it's a representation of maybe we haven't quite understood how matter couples to gravity. And that could lead to some evolution that looks like this dynamical dark energy. And so there's this potential strain, right? There's the ACT result, which is saying pretty much everything's consistent with lambda. And there's this dark energy survey result saying, DESI result, sorry, saying actually things are beginning to look like there's there's dynamical dark energy. The thing that concerns me a bit about the last result, the DESI result, is that when DESI just look at the data from their own galaxies themselves and don't add anything else, everything seems to be consistent with the cosmological constant. When they add in, they add in some cosmic microwave background data as well to pin some things down. Things get a bit more strained, but there's still sort of consistency. The thing that really begins to drive the move towards dynamical dark energy is when they use supernovae. And they use 3 different sets of supernovae. So these are, one's called the Pantheon set, one's called the Union set, and one's called the DESI 5 set. 3 separate sets. And these supernovae are made up of, each one's got 1,000, 1,600 supernovae in there. There's some overlap between them because they've looked at the same objects. But these are giving quite different degrees of evidence for the dynamical dark energy. They're not giving the same. Some are giving 2 sigma results, some are giving 4 sigma results. And then within each supernovae data set, these are made of different groups that have looked at small redshift versus large. I'm getting a bit technical here and I don't mean to. So all I'm saying is there is some questioning still about the supernova element of it and whether it's been rightly interpreted. There's no question about the DESI data, which is just this breathtaking data. It's the interpretation of how you're coupling the supernovae in with it. And it's important we get this right because from a cosmological standpoint, from a theoretical standpoint, it's a massive difference whether it's a cosmological constant or whether it's dynamical. And there's one final thing about the dynamical bit, which is causing concern for theorists. And that is, it's driving us into a regime of parameter space, of theory space, where we call it phantom dark energy. Phantom dark energy, I have a little link to that because it's the guy who came up with the idea of phantom dark energy is a friend of mine, Rob Caldwell at Dartmouth. And he was doing this work when we were both sharing an office at the Isaac Newton Institute. And I remember him telling me about it. And I was thinking, that's bonkers, because it's unstable. Phantom dark energy is such that it just keeps driving the acceleration faster and faster and faster. And in fact, the universe ends up going through what we call a big rip, and it kind of tears apart. But the data seems to be suggesting we're going down there into this regime. It's going phantom. Now, there are lots of ways of coming back up, so you don't end up shooting down. But at the moment, the fact is driving us down into this region is a worry. for theory people. They're saying we don't think this should be happening. There's quantum mechanical reasons why we don't want to be in phantom regime. We don't think it's consistent. So there are ways around it, but they're not obviously natural, shall we say. So there's lots of questions going on. Just to show the impact of DESI, the first paper that was released just on a year ago now, under a year ago, has got like 700 citations in a year. And in our field, that's huge. I mean, the CMB papers get this as well. But it's having an impact.
There's dynamical dark energy, which changes over time in this worrying but interesting way, or the traditional cosmological constant, which is consistent. But then you said to me that the cosmological constant changed over time as well. But like that was in a more
all right.
Like I feels like hang on, they're both changing over time. Just clarify that for me.
Yeah, thank you. Okay. So this is the difference between what we call the density, which is the energy per unit volume. For a cosmological constant, that's a constant. And the thing that's actually we tend to plot isn't the density, it's the density divided by what we call the critical density, which is another density. It's the density of matter that's required to give me a spatially flat universe. And what you find in that case, the one that I did that went up like that, it's that parameter. It is in fact, it's the sum of those parameters. It's the sum of this density parameter. It's called omega, big omega. Rho, which is the density, divided by the critical density. The sum of the omegas is 1. And it's that's actually always conserved. So the actual density itself for dark energy just remains a constant throughout. Well done. As I was saying it, I was thinking, what do I do here?
Okay, I wasn't sure. Let me ask you this. If it turns out that this DESI finding is heading in the right direction and dark energy is dynamical and changes over time, what will the implications be for someone like me? Not a theorist, but someone who is a fan of science and is really interested and hopes to have some basic understanding. How will my understanding of the universe have to change, that kind of interested layman?
It's going to mean that we've definitely got something new, a new particle of some form or a new interaction with gravity that we haven't fully explored. And so it would mean that the consensus, which has been there now for over 20 years, that we understand this as a cosmological constant plus cold dark matter plus baryons, isn't the whole story. And I'd have hoped and I'm sure for someone like yourself, you'd find it interesting to know there's stuff out there that we don't yet know, and it's worth going out to try and explore and find out, because that's the nature of human beings. That's what we want to do.
But we already don't know. We already don't know what the cosmological constant would be. So it turns out the thing that we didn't know about, it turns out that's not there at all. Well, there's something else we don't know about instead.
It's a good point. And in fact, not only, it's actually worse than that at some level. The cosmological constant has this problem. And the problem is what we observe it to be, if it's lambda CDM, is much smaller than what we would naively expect it to be. And a number of us, and Tony, for example, and I've written it with Paul Safin and Tony and Christos, have tried to come up with arguments as to how we might explain away the cosmological constant problem. The dynamical dark energy doesn't explain away that problem. This issue over the differences, and what in my head I'm hoping is that there's perhaps a symmetry of nature that we haven't yet figured out, which forces the cosmological constant to be 0. It's just not there because symmetry doesn't allow it. And then, but the dark energy is there. We measure it, and so the idea is then that the dark energy is represented by something else. But I take on board you're moving one unknown to another unknown. In terms of the cosmological constant, what a number of us try and do is we try to understand that there must be some fundamental origin maybe in a cosmological constant. And so you go back, for example, for those of us who've worked on it, it's a string theory, where you look for terms that are present that could act like this constant contribution. And they're there in string theory, they can do it. What we can't yet figure out is how to determine their magnitude, but they could be there.
I think the brain problem I've had for a long time that I'm struggling to overcome is I've always thought as the cosmological constant as a number, like pi. or just like an abstraction. But when you say cosmological constant, although there are numbers attached to it, you are talking about a big bunch of stuff.
Yeah, it's something.
Yeah,
it's
like
something.
It's a physical
it's
thing.
A thing. It's a thing. Yeah, and it's here. Hi.
Yeah.
Why don't you show yourself?
Yeah, it's not like pi. Pi isn't here, but pi is a constant.
No, it's here. Yeah.
Okay. Is the fact that dark energy could be dynamical and have changed over the history of the universe an inconvenience for you? Because when you're coming up with models about how the universe...
No, I love it.
Yeah.
I love it.
But you've always... But it makes your job easier if it is consistent.
Yeah, I mean, it's true. You can solve things easier with a cosmological constant. The equations you have to solve become more readily... you can do integrations better. But the prospect of using observations to test a fundamental quantity like a new scalar field, just I think is fantastic. I have to say I'm not yet convinced it's there, but it would be nice if it was. And as I mentioned briefly, that intriguing little line in the ACT paper, which basically says everything's cosmological constant, don't worry about it, does have this one little line that
but maybe it's not.
It says, okay, moderately better fit. And I'm thinking, what? What's going on? And so I'm going to try and talk to some of the people. I've got a good friend, Joe Dunkley, who's involved in this. So I'm planning on an email to Joe saying what's happening here. Is now placed. And it was built for another large accelerator called LEP, which is the Large Electron Positron Accelerator. So that large because it's so big, 27 kilometers.
So which spokesperson do you give it to? Do you give it to the spokesperson that was in charge, when the discovery was made? Do you give it to the spokespeople who sort of came up with the idea of the experiment?